Hi, this is Planet Wayne here with another example on how to use a programmable Rednet controller, and in this case we're actually creating a countdown start line. Now, fairly simple construction, single controller that's been expanded to 17 programming slots, and again that's using two LX500s and one LX100 expansion card. We've got a simple control surface over here on the left hand side of the controller with a reset button, an instant start button and also a delayed start button, and they're coming in on the left hand face. Our actual connections for all the lamps are coming in on the right hand face, and we've also got this tripwire as well that we're using for picking up on a delayed start, a false start. So if somebody tries to cross the line before the actual countdown started or before these green lights are on, they'll trip on the tripwire. That'll register in the controller and we'll get a different sequence coming out the top there to indicate false starts. And then out the back here we're also using the red note blocks from the Mindfactory Reloaded mod, and again, although I've got three, these are actually quite unique in the fact that the tone that they produce, or the note that they produce, is very dependent on the value that's being passed through the connection from the Rednet cable. So the higher the value through there, the higher the pitch of the tone that comes out of there, and you can actually, if you take that value up past the normal sets of tones, it'll change the instrument as well. So you can even cycle through the different snare drums and bass sounds and various other bits and pieces that you'd normally get depending on how you place a normal Minecraft note block. But yeah, simple thing with that, just three connections on there on the different colours that allows us to actually use one note block to produce all of the tones. The only reason I've got an extra two on the back is I was playing around with different volume levels and such like, and it just actually sounded a little bit louder having more note blocks producing the tones at the same time. So no need for it, but if you just wanted to add a bit more volume to that, then that'd be the way to do that. As I said before, note blocks are coming in through the back face, control panel in through the left hand face, and the right hand side of things is picking up all the lights that actually make up the start line there. Now the actual lights themselves, we're using the Project Red illumination lamps that we've used before with these things. These are all powered from the Rednet cable, so the green lights that we've got at the bottom here are all coming off the light blue channel. The red lights that we've got across the top here are actually being powered by two different functions within the controller. So when it's doing the normal countdown, we're using white, orange and pink there, or magenta I should say, sorry. But when we've got a full start, we're actually using the light green or lime green and yellow. And the way that works is we're feeding a block here behind the lamp, so whichever one is actually activated is the thing that then is going to fire that lamp off. So we can effectively drive that lamp from two different channels there. And again, that's just repeated exactly the same over this side, nothing special on that one, exactly the same colours, and that all gets connected underneath the start line back into the right hand face on the actual controller. So that's basic construction, nothing too flashy going on. If you wanted to move the control panel, obviously we've got that delayed start there, so the idea behind that is if you actually wanted to start the race because there was nobody actually standing here, you could hit that one, run back to your vehicle, get in and get ready for the countdown, and then away you go. As I said before, we've got a reset button which just resets everything back to normal, and then there's the normal start or instant start which just takes it straight in. Now that button there is just so I could just do a quick simulation of what would happen is if you broke that line, and we get that different flashing pattern across the top there. So that's not actually needed, and neither is the lamp there, but it was just put in just so I could demonstrate the fact that that tripwire is actually providing a different sequence if it gets tripped before this green section comes on here. So if you've got somebody trying to jump start the race, you'll know about it because, as I say, it'll just change this light sequence across the top there, and everybody else will know that somebody's jumped the line there before you've had before everybody was ready. So yeah, just a simple addition to that one. That's it from a build point of view. Real simple construction here. It was just something to show you the example on this. But as with all these things, the main thing is actually with the coding in the controller. So without further ado, we'll break that down and I'll show you how it's all put together. We're sat here now on the programming interface on the Rednet controller, and as I said previously, with the expansion cards that we've got installed in there, we've got the total of 17 slots that we're using here. Now there is one right at the very end that we can drop out if you didn't want to make that last expansion card, but in doing that, that'll actually reduce the functionality and get rid of the delayed start on there. So yes, it's only taken at one slot, so if you needed to get rid of it, if you knew you were always going to be able to hit go and then get to your vehicle or get ready for the start, then you could drop it down by that one slot. So not so key, but just made a nice inclusion on this one, just to sort of add a bit more functionality to it. So here we are on slot 1, and the whole thing is driven from this multipulse generator that's in this first slot here. And the way that works is that's taking its start trigger from the left hand face. This CLK value here is set to IOL, and that's on the white channel. Now if you remember back from our control board that's in the side here, that white button, or the button that's on the white channel, is our instant start. So basically when you press that, it starts this to count for a period of 5 pulses, which is where this CNT value is here. And then there's various delays here, so we've got T high and T low, which governs how fast it pulses out those 5 ticks effectively. And it's doing that, and it's pushing the output of that into variable 5. Now variable 5 will get used into a counter in a little bit in a later slot, and that's the thing then that we're using then to be able to select where we are through the start sequence and so on. Now you might think, why are we actually counting 5 pulses instead of just the 4? And the reason behind that is we actually want to zero the counter back to, or put the counter back to 0 when we've finished the whole of the start sequence, and that's what that extra pulse at the end does there. So when you effectively get to the end of a counter value, to get it back to 0, you sort of wrap it back, or send it another pulse and it'll wrap it back to the start point. And because we don't want to do anything whilst the counter's at 0, that's an ideal thing then, just to leave that alone, just sort of so it's sitting there effectively idle and not doing anything. So that's why we've got 5 pulses in there, even though the actual start sequence in itself is only 4 items long as such. You've got the 3 with the individual red lamps across the top there, and then there's the extra 1 for firing the green lamps and so on. So again, just a thing just to be mindful of. That's why we're counting to 5, and that'll reset the counter that we'll get to in a second. Right, this is slot 2, and this is where our counter is basically. We're taking an increment from variable 5, which we've just been using in the previous slot there. We've got a constant value of 5 set to the maximum number of digits that, or maximum value that the counter will count up to. We're also resetting this from an IO line, again coming in the left hand face, which is on our orange channel. So again, remember that orange button that we've got on the left there, that'll reset this counter back to 0. And then the output from that, or the actual value of the counter, gets pushed into variable 0. And again, that gets used in the next slot to be able to tell or set other variables to feed the rest of the programming logic on there. Okay, here in slot 3, we're actually making use of the demux 16out analog function. Bit of a mouthful this one, but basically what this will do is, depending on the input on S here, which is coming from variable 0, it will actually take an input value that I've got set to a constant value of 9, and depending on what the value of 0 is here, we'll actually push it out to one of these 16 slots on the right hand side. So if you remember, the counter that we've got is set to wrap through 5 different stages. We're not doing anything when it's on 0, so typically if the system's idle or nothing's happening, the counter should actually be on 0, and we're not doing anything with that. But as it steps through, we're actually taking that value that's been set here and pushing it first into variable 1, then into variable 2, into 3, and then into 4. And then each of those gets used a bit later on to set each of the different values for the or set the lights to come on in sequence and so on. Now, one thing to remember with this one, this value that we've got here, this constant value of 9, we're also using that to set one of the tones on those red note blocks. So if you want to adjust the tone for the for the red section on the redstone blocks, or red note blocks, then this is where you'd adjust that value. Obviously increasing that value will raise the tone up, decreasing it will make it lower, and as I said before with those red note blocks, if you go past the normal scale that you get for the tones, you can actually start to select different instruments. So you could have a snare drum or a bass drum, or with the various other tones that you can get out of a normal red note block there. So that's where that's being used, and as I say, each of these variables then gets used in the next slots to set the various latches to keep the lights on as we're working through the start sequence there. Slots 4 through 6 are basically using this SR latch function. Now, these get set depending on the variables that we've set previously, and get reset on variable 9, which we haven't got to yet. So for each of the lights, or for each of the red lamps in sequence, we've got variable 1, which sends out to IO on the right face for on the white channel. Next one is variable 2, and that's again out on the right for the orange channel. And the last one on this set is for variable 3, and again that goes out on the right hand face on the magenta channel, and that's basically setting a latch. So once this thing's set, the lamp stays on until it's reset effectively. So that's basically the function of an SR latch there, and that covers each of the 3 red lamps that make up that first part of the start sequence there. Slot 7 is the another SR latch, but this time it's a gated version, and I'll explain what that difference is in a second. But this is the thing that actually then sets the green lamps for go. Slight variation of where we're resetting from. We're actually resetting based on the content of variable 8, which we haven't got to yet, and we're setting when we're reaching step 4 in our count sequence. So effectively we've gone through the first 3 red lamps, then we're going on to this onto the green lamp here, and that's where it's getting set with variable 4. Now the reason that this is a gated latch basically is this will only work if variable 7 is also enabled. And again, we haven't quite got to the setting of that variable yet. That's a little bit later on, but it's actually used as part of the detection as to whether anybody's tripped that start line tripwire that we've got there. So if somebody's trying to jump start before we've actually got to green, then that changes the content value of variable 7 a bit later on, and it will actually stop us from setting the lamps to come on, or setting the green lamps to come on if somebody's done a full start. So hence the fact that we're using a gated latch here rather than just a normal SR latch is because we only want it to be available when that tripwire hasn't been tripped. Now the output for that is coming out on the right hand face again, and this is out into onto light blue, but we're also filling variable 6 as well with the inverse version of this. So again, variable 6 we haven't quite got to yet, but basically that gets set when the green lamps aren't on, and again we'll get to that as we get further through the programming logic on that one. Here in slot 8 we're using a 3 input OR gate, and the input for that is coming from each of the left hand faces on each of the buttons that we're using. So we've got white, orange and magenta, and the output from that gets pushed into variable 8, and if you remember from the previous slide, that's the thing then that resets the green lamp. So basically, in essence, if we press any button on the left hand side of the controller, that'll reset the green lights just to make sure that they're off before the whole sequence starts again. So that's slot 8, and that's what we're doing on that one. Slot 9 is what we're using to reset the red lamps. Now the way that we're doing that is with a 2-input OR gate. Now one of the channels on here is the I/O channel coming from the right hand side on the light blue face, or light blue channel, and if you remember, that's the thing that gets set when the green lamps go on. So as soon as we get a green lamp, we're going through this OR gate here and we're setting variable 9. Now if you remember, variable 9 was used in some of the earlier latches that we got in the sequence here, and they are the reset, or that's the reset variable that we're using to turn those latches off. So of all the red lamps that we've got, or the 3 red lamps that we've got across the top of our display, this is where they get turned off. So as soon as the green lamp comes on, that sets variable 9, which then resets the red lamps. Now we're using a 2-input OR gate here because we're also using variable 11 for the other side of the input. Now variable 11 is set when we detect a false start. So when that tripwire gets set, this gets set a little bit later on down the road, and that's another reason to reset those red lamps across the top. Now if you remember from the opening sequence there, if we do get a false start, then instead of those red lamps all staying on or counting up in sequence, the sequence then actually changes to the 2 left, or the left and the right lamp of the 3 flashing alternatively. Now we can't do that if the SR latches are set, so again this gets used to reset those latches, but then there's another function a bit later on that we're actually using to make those 2 lamps flash alternatively, so we don't have to worry about having latches set to do that part of it. That's handled a bit later on through the sequence there. So this bit basically is to reset those red lamps as we're progressing through the sequence there. Slot 10 is another SR latch, and again it's the gated version, and this is being used to is actually being set when we're detecting a false start. So the input for this is coming from the right hand face on the pink channel, and if you remember from our build, that is basically has the tripwire set against it. So as you're going through the system, if somebody hits that tripwire, this is where it gets latched. It's reset from variable 8, so that's any of these buttons that get pressed on the left hand side here, and the output for that is going into variable 11. Now the other things to remember with this, because it's a gated latch, this only works when this E or enabled line is set high. Now that is coming from variable 6. Now if you remember variable 6, that is the inverse of the latch that's controlling the green lamps. So as you're going through the sequence there, as long as the green lamps aren't on, variable 6 is high, and that gives you the ability to detect a false start. It's pointless detecting a false start if the green lamps are already on, because obviously the race or whatever it is that you're doing here has begun and everybody's on the way, sort of thing. So that's why we're using an SR gated latch here. Again, it just makes sure that this thing only gets set as long as the green lamps are not on. And then, as I say, the output for that gets put into variable 11, and the inverse output for that is put into variable 7. So that's slot 10, and that's what we're using to detect the false start on there. Here in slot 11, we've got a simple wave timer or wave square timer function that we're using here. The values that we've got set for the timer is a constant value of 5, and that's getting pushed out into variable 10. Now this is actually used to control the speed of the lamps that flash, the red lamps that flash left and right when we've got a false start. So if you want to increase the speed that they're flashing at, or if you want to make the pulses between the flashes longer, increase or decrease that value accordingly. And that gets used a bit later on when we start flashing the lamps around and so on. So this is a timer, typically it's always running, but you never see the output of it until other conditions are met. So as I say, simple square timer or wave square timer, which is being pushed out into variable 10. Here in slot 12, this is what we're using to alternate the flashing red lights when we've got a false start. Now we're basically making use of this pass-through function, but the ring variety. Now what that basically means is for every time the clock counter gets set, it will step through each of these values until it gets to the end and then come back to the beginning again. Now we've got a restriction set on this one, so we've basically got a value of 2 set against this CNT value here, which basically means it will only count two outputs. So it'll basically in this setup will alternate between this 0 and 01. Now the output for that is going on the IO line on the right hand face, and it's on the lime green channel and on the yellow channel. Now if you remember from our build, those are the two extra channels that we're using on the left and the right hand illuminators that we've got on the red lamps there. So that's how we're doing that one, but the input for these, because it's a pass-through, the input is actually coming from variable 11. Now if you remember a couple of slides back, variable 11 only gets set when we've got a detection on the full start latch. So as soon as that gets set, that then passes through on these two channels here, and gets alternated based on the fact that that clock is just constantly ticking between the two. So hence the fact that when variable 11's not set, we've not got any interference on those red lamps at the top, because these two values just aren't getting set. So quick and easy way just to be able to alternate between two lamps flashing, if you need to make sure that that only happened when there was a specific variable set or when there was a condition set. So you can use that there on the input of this pass-through to actually achieve that. So again, that's what we've got in slot 12, and that's the thing that actually makes those two red lamps flash alternately on the start line there. In slot 13, we're actually using a maximum 3 input function. And the way that this would normally work is if you have 3 different variables coming in here on each of the input lines, this function would actually pick the highest value that it's contained within them and push that to the output line here, which is going into variable 12. Now the inputs that we're using on here for variables 1, 2 and 3 all actually contain the same value. If you remember right back at the beginning where we're talking about the demux function, these actually contain the value that we want to set for the note block to play out the back there. So it's just a simple, a quick and easy way of being able to get effectively 3 inputs coming from 3 analog inputs rather than 3 digital inputs, which you'd normally use an OR gate on, and just carrying that value straight through and pushing it into another variable, and that'll get used in the next slide to actually start the tones out on the note blocks that we're using on the back of the controller there. Slot 14, we've got another multi-pulse function. Now this one is being used to generate the pulses on the tones for each of the red lamps that flash on as part of the start sequence. So the trigger for this, or the input value for this, is coming off of variable 12, which we just set in the previous slide. The start pulse for this is coming from variable 5, which is off our main multi-pulse function right back at the very beginning. And we're actually doing a count of 5 pulses on this. So if you needed to increase or decrease that, again depending on how you want to do the timing with this, that's where you could adjust how many it does, and this is where you'd adjust how fast it does it. And basically in this example we're running it as fast as is possible with the controller here. So this is 5 rapid succession pulses that are being generated with a value that's coming in from variable 12, and the output for that is going in IO line off the back face, and that's off the white channel. And again, if you remember, that's connected to one of those note blocks that are off the back of the controller there. Slot 15, and we've got another multi-pulse generator, and this one is to do with the tones that get generated when the green lamps come on also. So we've hit go effectively. The input for this is a constant value of 21. Now this is quite key in so much that the higher the value of this, the higher the tone that comes out of the note block. Obviously the lower the value, the lower the tone that comes out. It gets triggered from the IO on the right hand face from the light blue channel, which if you remember is connected to our green lamps. So as soon as the green lamps come on, that fires this multipulse into action, We've got a count of 15 set in there, so we're getting 15 pulses. And we're basically again generating them as fast as is possible, with the T high and the T low values both being set to 0 on here. Now the output for that is going through into the I/O face on the back channel again, and that's on the orange line, which again is connected to those note blocks that are attached to the back of the controller there. Slot 16 is another multi-pulse generator. Now this one's being used to generate the tones that that gets played when we have a false start, or if somebody trips the trip wire across the start line there. Now the input for this is a constant value of 1, so it's the lowest note that we can generate with those note blocks there. The clock or the start pulse is coming from variable 11, so again that's coming off that latch that we'd set a good few slots ago now. And we're actually doing a count value on this one of 10, so 10 pulses or 10 notes. This time we're slowing it down a little bit, because obviously it's a bit of an error condition, or a bit of a sort of false start condition that we're signifying this, so we don't need to push these through as fast as possible. So for each of the T high and the T low here, we've got constant value of 4, which seems to fit the bill for the example that we've got here. Now the output for that again is on the back face, the same with all the others, only this time it's on this purple channel there. We've finally made it to the last slot, which is slot 17, and this one is just a real simple delay function that's basically taking the input from the left hand face on the purple channel. We're delaying it by a constant value of 60, and we're pushing the output from that again into the left hand face and onto the white channel. So this is basically how we're cheating the fact that we've creating a delay with that purple button there. Effectively all it's doing is it's pressing the white button, but it's pressing it 60 ticks later effectively. So again, real simple thing to just add a bit of a delay in there. Obviously the longer you make that value, or the higher you make that value, the longer the delay, and subsequently the lower the value, the shorter the delay before it actually pretends to press this white button. So a real easy cheat just to add a bit of a delay into the start of the process there. Just before we wrap this one up, I just wanted to show you this other variation of the build, and this one's using the standard note blocks from Minecraft there. Again, the only real difference between that and the one over there is typically we're going to definitely need 3 note blocks. The reason being is you would have to set the tones of these now in this traditional way by sort of right clicking on them to go through the tones and so on. Again, hence the fact that we need the three note blocks there, and as long as the colours all match up to the bottom there, so we've got the white, orange and the magenta colours, they'll work fine with this controller. Again, I just wanted to show you the fact that we can use these instead of the note blocks and so on. The only thing to be mindful of is typically you will need to space them out, because you will get interference if you put them all together. This centre block will certainly power each of the 2 either side of that one there, so again, just be mindful of that one. But from a normal operational point of view, if I start the process off, they'll work just as well, and you also get the little animations bits and pieces coming out the top of them as well. So again, if you wanted to do that, that's certainly a possibility there. That's it from me, Planet Wayne. Hopefully you enjoyed the video. Again, likes and comments in the sections below are very much appreciated, and I shall catch you next time. Thanks a lot, and bye for now.